It's a great pleasure for me to introduce Salim Roukos, who will give the invited talk for today. Salim is a senior manager at IBM research group in Watson. His main interests are in the area of machine translation and information extraction. He has been involved in several quite popular projects, big projects in the States, including the GALE project. And today, Salim will talk about recent advances in statistical machine translation. Thank you.
Thank you, Bernardo. Good morning. I'm curious to see how many of you work on machine translation right now. If you could raise your hand. A little bit, okay, very good. Just to get a sense. Very good. So I'm gonna start first by doing a small advertisement. IBM made a big decision earlier this year to start a new division called the Watson Group, which is focused on cognitive systems. So I want to tell you a little bit about it before I start talking about statistical machine translation. So they're gonna open a new headquarters in New York City. And it's in an area called Silicon Alley, which is a place where NYU is and a bunch of companies also. And the concept is to operate like a startup without the startup resource constraints. All right, so let's talk about language understanding. Language is very, very ambiguous. It can be quite tricky. So these are example sentences that are interesting. Noses that run and feet that smell. Ship by truck and send cargo by ship. How can a slim chance and a fat chance be the same while a wise man and a wise guy are opposites? Okay? So language is really extremely subtle, and then you have to worry about all the bits of information to sort of make a decision of what does a sentence really entail. So if you have a question like Welch ran this, or what did Welch run, you may have a structured database that tells you that Welch is the chairman of GE, if you have a structured database. But a lot more information is available in freehand or what we call unstructured text. And this is an example sentence that's quite tricky. If leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. So it's a quite tricky sentence to get that relationship. Now, to really answer questions, and complex questions is what we mean here, you need more than keyword evidence. So this is an example to compare and contrast. So if the question is, in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India, and you figure out, I'm not going to describe the system, obviously, but suppose at the end of the day, you found a piece of evidence for some answer, and you want to see, does this piece of evidence support the answer? So this particular supporting evidence sentence, you might superficially think it's matching because a bunch of the words or keywords match, like celebrated and celebrated, and May 1898 may match May, and anniversary may match 400th anniversary, and Portugal matches in Portugal, and India matches India. And you might then infer that this evidence supports the answer Gary is the one who is the explorer. But clearly this is a wrong answer. What you need is a fancier system, which is what was used in the Watson system for the Jeopardy game. And what you need are not only text matches, keyword matches, but a lot of other ways of matching things. So in particular, you want to have a paraphrase system that matches arrival in with landed in. You want to do a date match that May 1898, 400th anniversaries matches 27th May 1498. So reasoning about time is quite important. And you also need some geographical database to realize that Kapat Beach is located in India. So you need a lot of different pieces of information, and you have to combine all this in a probabilistic model, and you have to train the probabilistic model to find a confidence score that Vasco da Gama is with high confidence in answer to that question. So we have defined cognitive systems, and this is an area that IBM is investing quite a bit in for the next few years. And the fundamental definition, even though I don't believe in emulating the human mind. I am a much more machine learning type of person. But the spirit of the concept is try to solve problems that are more the kinds of problems that we humans are very good at. Okay? And in that sense, Watson is an example of a cognitive system. The system understands language and tries to make inferences between different sentences, how they relate to each other. It, at least in the Jeopardy context, it demonstrates human-like accuracy. So in that sense, that's quite an achievement. Even though it does not necessarily use anything that humans do, right? So I feel that's an important distinction to keep as we discuss these cognitive systems. And finally, because it's a computer, it's a machine, it can do things much faster over larger quantities, so eventually this will give it a significant advantage over humans, potentially. So that's the advertising. And actually, I'm part of this new effort, and I'm really quite excited. So in terms of our focus, is not only are we building Watson systems for many domains in English, we also are working on other languages. And that's really where I'm mostly involved now. All right, so now I'm going to come to the talk. And essentially, I'm going to talk about statistical machine translation. And I have 4 topics, 3 main topics, and a quick one, the last one, text leveling with MT. I'm just going to give you a brief summary. There is a paper in the proceedings where we wrote quite a bit of details about what we did on text leveling. But for the purpose of today, I will just give you the high-level result. And for those people who are interested, can dig into it by reading the paper. So the first topic is text-to-text machine translation. IBM celebrated its 100th birthday 2 years ago, and they identified a bunch of technologies as milestones for IBM in IBM's history. And machine translation was one of the icons. IBM had started working on machine translation in the 50s, on Russian to English translation. So, I mean, we have a number of accomplishments in the machine translation field, including the development of statistical machine translation. But at least from an IBM perspective, it's not easy to show up, right? Because, IBM is such a big place. Any core technology is small in the scheme of things. So this was quite an accomplishment for us. So I'd like to highlight 3 use cases for machine translation. Text-to-text translation. Text comes in from a source language. You translate it into a target language. If you add speech recognition from the source language to source language text and then text translation, you do what we call speech-to-text. So for example, if you have a broadcast news program on TV, you recognize the speech and translate into the target language of the user. That's very useful for me upstairs, right? I don't really know Czech. It would have been nice to have closed captions in English, even though if it's machine-produced. This way I get a sense of what's being discussed. So we have systems like that. And if you add on the target side text-to-speech synthesis, now you can build a speech-to-speech system. You speak in one source language, convert to text in the source language, translate in the target language, synthesize in the target language. That's one-way translation. And you can translate the other way, which we refer to sometimes as two-way speech-to-speech translation. So the thing that is common to all the work I'm going to talk about is called statistical machine translation. The idea is we will learn from a parallel corpus a statistical model to translate from one language to another. And the basic premise is you find documents that are translations of each other by humans, and then you figure out ways to align them at the sentence level, at the word level, at the phrase level, and from there you extract a statistical model. This is very important for 2 big reasons. One is you can go to new languages quickly if you can find a parallel corpus. And the other one, equally important, is you can customize the machine translation to the domain if you have translations from that domain. Language is a very big space. So you will discover very quickly that by customizing the machine translation to a specific domain, it will do much better in that domain. Technical documents are very different than news documents than blog postings. So this notion of adapting to a domain is another big advantage of the machine learning statistical machine translation approach. So this is a slide showing progress. It's very important to realize that continuous progress, even at a slow rate, can be significant. So this is a great example of this. So machine translation actually, as I said, is an old field. People have been working on it for over 7 decades. But in about 2002, a new automatic metric was invented called the blue metric. And I have some results using the blue metric And a new DARPA program started then called TIDES, where we are showing the performance improvement. Higher is better. This is blue. And over the years, from 2002 to 2007, you can see there is a steady progress. And I remember during those days when I used to show the curve here, people would tell me, oh, it's going to saturate. And I wasn't saying one way or the other, but it hasn't saturated. It really has been improving at a reasonable rate. Then in 2006, DARPA decided to, this was Newswire on the left, to generalize to Newswire, news groups, broadcast news, which is well-spoken, and broadcast conversations that were reasonably good. Okay, not the most informal. They were still reasonably good, but they were conversational, like an interview. So as these domains are more challenging, and the metric was changed, instead of measuring using the blue metric, the automatic metrics, they wanted a human translation error rate, which basically says, take the output of the machine translation and edit it by a human so that it gets the correct meaning as intended, and measure the percentage of the edits. So that's called human translation error rate. So the percentage of the edits was in the 17% for Newswire, Arabic Newswire, the red curve, and then it decreased over a period of 4 years to about 7%, human translation error rate. The key message really is that things are improving every year. I think that's really the only important thing. You cannot trust neither the slopes nor the absolute values because the details matter. Because if you change the content, the curve changes, right? If we go from Newswire text to Arabic weblog, which is the green curve, you can see the error rate is almost triple. Oh, double, sorry, 15. It's almost double. So the performance will move depending on the difficulty of the domain. But what's important is over the years, the technology is improving continuously. And more recently, DARPA started a new program called BOLT. The top two curves are Arabic to English. The bottom curve is Chinese to English, just to show, another language. And here the metric is not the official DARPA metric. It is what we use internally for our development. It's TER minus blue. It's averaging the two metrics because we don't trust either to predict H-TER accurately. Even this one is not a whole lot better. It's only a few percent better, but it's a safer optimization metric. So lower is better. So it's like negative blue, if you will, TER minus blue. And you can see again over a period of 4 years, actually these results are off the press like last week. We do internal dry runs. You can see that things are improving. Now, we have many different technologies, and we can get to those details, but the high-level message is there has been a steady progress in machine translation over the last 15 years. Okay, I want to describe a little bit our best Arabic to English system. It's essentially what we call a direct translation model. It basically says, after I've translated some pieces of the sentence, I have to decide what's the next word I want to translate in the sentence, and what should its translation be. So this is the next position J in the source sentence, and its target translation W. And it depends on the history, which is what have you done so far. And you can throw at it a lot of features. So this is a global maximum entropy model, where we can throw at it as many features as we can think of, that we can train. And we have enough training data to train, accurately. And our system has millions of features that are trained simultaneously. I don't want to get into the details. We support what's called discontinuous phrases, but let's not get into this here. And you can always annotate the input source sentence with any annotation you want. You can say this is a name, this is the parse tree, so you can add what we call additional streams of information on the source sentence. So all this rich analysis of the source sentence can be used in the definitions of the features of the maximum entropy model. So I'm going to illustrate for you one example where we use the parse structure to improve the performance of Arabic English translation, and that's actually a real significant win from a human assessment of the machine translation. So this is an example sentence where Arabic is from the top to the bottom, and the translation by the machine on the right-hand side is the English. He visited a number of bakery owners of ration areas. Now, what's interesting is we're showing also that this word produced he visited, right? So this is a 1 to 2 phrase, and this is 2 to 3 phrase. a number of, right? But what's interesting is that this is really bad, and that's a typical error in Arabic to English translation, because Arabic, it's a VSO order. Okay, so introducing false subjects out of nowhere is not a good thing, and that happens with many machine translation systems out there. Now, if we look at the parse tree, it's a very odd way to display a parse tree, but it's down this way. You can see that we know there is a verb, and the subject phrase is from 2 to 5, which is a number of bakery owners. That's the subject phrase in the Arabic. So if you have a feature that says, did I translate the subject phrase before I translate the verb, and it gets its probabilistic score, then you will tend to put the verb in the right place, hopefully, if the parse tree is correct. So that's the notion of how we add features to our maximum entropy model. So by adding that feature, which is what we call the parse label features, we discovered that the word visited now moves to after a number of bakery owners. It goes to visited. So we moved over the subject phrase, essentially. Okay? Now, it's not perfect. We still have work to do. We screw up this content word here. We make it the. That's another classic problem with statistical machine translation. A lot of content words tend to be converted into function words. It's not that simple, because sometimes you want to drop content words. So it's a tricky problem. So we still are working on this one. Okay. All right, so we evaluated the system this past May on Newswire text, and we compared it to an online system. And the evaluation is, in this case, 113 sentences evaluated on a 6-point scale. 0 means nothing is coming through. You don't understand what's being said. 5 means it's perfect, that the English is really perfect. Okay? And we compared this DTM system to an online system, and you can see that on average, the score is about 2.9 versus 2.6. So it's about 0.3 better. And 0.3 doesn't mean much for you, but I know what 0.3 means. It means at least a year of work. Okay? Or a little more, depending where you are in the operating curve here. Now, we usually say that 3 is the minimum for quality in terms of comprehensibility to a human, but this is misleading because in Arabic to English, Arabic sentences tend to be paragraphs, like 50 words is a typical sentence in Arabic. Okay? So when a human is assessing a 50-word sentence, any few problems here and there, they tend to punish harshly. So it's really much better than this score would indicate. It's because of the nature of the size of the unit. Okay? But we can leave that to a small technical discussion if somebody's interested. Before I show you the output of the system, wanted to just give you a little bit of a summary of what we are doing in the last 3 years now, 2.5 years, in the BOLT program. So the focus is to go on informal content, meaning discussion forums, chat, text messages, anything that's communication-oriented. And DARPA has been focusing over the last 10 years on both Chinese and Arabic. This has been true in the previous program, TIDES, GALE, and now BOLT. And they added a dialect, because when people converse, as opposed to speak in broadcast mode, they use then their dialect. Nobody speaks MSA, even though on TV they speak MSA. When two people speak in Arabic, they will speak in their own local dialect. And in this case, they picked Egyptian as the focus language. There are probably 20 or 50 dialects, depending on how you define dialect in Arabic. And to contrast with the previous program, I think the big difference is when it's conversational, you typically get shorter sentences, less than 15 tokens, whereas the other stuff is much longer, more than 25 tokens. And the other big difference in this last 3 years is that DARPA wanted us to deliver a system that runs every year. In other words, we run the evaluation, we also give them a system that can run on their own. So that puts pressure that the research system has to be fast enough to be a practical system. So we evaluated our BOLT system. This was done 1.5 years ago, maybe actually almost 2 years ago, November 2012, on 50 sentences. It's again comparing the IBM system to an online system. And this is on Egyptian Arabic. It's no surprise that we are much better than the online system because this is Egyptian dialect, so we have customized to that domain, whereas the online system doesn't really know the dialects. So that's an easy win, if you will. But on Chinese, it's informal language. It's not dialectical as much. It's much better because we are tuned to the conversational style of language structure. Okay, and there, it's also the IBM system is better than the online system. Surprisingly, the dialectical Arabic is worse than the Chinese, even though in general, Chinese is much harder than Arabic, MSA. But Egyptian Arabic informal is harder. So this is why it's very hard to know. You have to know all the details to sort of make an assessment about quality and challenges of that nature. The way I summarize it is Chinese is about 4 to 5 years behind Arabic in terms of the quality of machine translation, based on the systems we have and the demos that we have. So I wanted to show you an example of some of the things that compare the online system with the IBM system on a document, just to highlight the things I mentioned earlier. So if we focus on the second sentence, or to be more precise, we call them segments because the concept of a sentence is not clear. As I said, in Arabic, they speak in paragraphs. So the second segment, the online system put the verb at the beginning because the Arabic had the verb at the beginning. Whereas the DTM system took this whole phrase, the National Alliance to Support Legitimacy, supportive of the Muslim Brotherhood group in Egypt, cold. So it was able to find the subject phrase, essentially, and move the verb about 15 words to the right, to put it in the right place so the sentence is more meaningful. Another example is in this area here. So this is the second, there's another segment. As I said, they're very long sometimes. So if we focus on this red region here, the head of bayonet in Marsa after the overthrow of massive popular protests. Something that's, I cannot say what caused the improvement because we have a lot of features, including the parse structure, but all of it together produces something like the spearhead in ousting Morsi after mass protest, which is much more meaningful. You know that El-Sisi is the spearhead in ousting. And finally, the last phrase here, lure of mercy, there is a decision here that this is probably a name and this is the spelling, and this is another way. So you can notice that the names are spelled differently. Mercy here, Morsi here. In this case here, in our case, we got lucky, we spelled it the same way, but no guarantees, okay? I'll tell you something. It's all there are lots of things you can fix in machine translation. So it's a question of when do you want to solve what problem. So consistency of name translation is really a small problem in the scheme of things. So we're not really ready to spend the energy on it, even though we have ideas of how to do that. Okay, so I wanted to show you a demo of the system. So I'm going to go get an Arabic web page from the BBC site. I notice it takes like 10 seconds to get the Arabic page, but it will show up eventually. It's trying to retrieve it. So it's trying to get the Arabic. It's getting the Arabic. When it becomes bold, it will get the page completely. It got the Arabic. Now it will translate it. Okay, so we can read a couple of sentences. Obama has the authority to organize fighting Islamic State without the approval of Congress. To organize the fighting might be a little better. But you see, it's pretty good from a meaning point of view. This system is 90% plus in terms of accuracy on newswire. So we can read another title. France organized an international conference on security in Iraq. My guess, I don't know, we have to look at the Arabic. Maybe France will organize as opposed to organized. Then there is somebody here, the death of Abu Ala, Iraqi assistant leader of the Islamic State. So that's reasonable. Let's see. There was one thing I wanted to mention, but maybe I forgot to do it. Let me see if there is a phenomenon like this here. Oh, okay. So sometimes we don't get the pronouns right, but here we got it right. Obama gets congressional leaders on his plans for a massive. So you might get its plans sometimes, right? So again, I would say name, consistency, co-reference resolution, those kind of document-level features. We have some of them, but we don't have a big onslaught because there are lots of potential other errors. You know, we're almost getting there, I would say, on Arabic. So now it's probably good to do it on this kind of context. It's not so good to do it on Egyptian, which is where we are focused right now, because there are lots of other errors, and it's not worth adding this complexity because the value is very small compared to other problems. Okay. All right. So before I switch to speech, I want to mention that we have deployed machine translation inside IBM for IBM, for IBMers to translate, so they have a portal inside IBM. We also have deployed it with customers for patent translation. And another big activity we've been doing is the use, and I'm going to talk quite a bit about that later in the talk, is on the use of machine translation to assist human translation, which is called machine translation post-editing. So this is the internal system. It's called Influent. It's a crowdsourced name. People voted, and they decided that's the name. It's a system that allows people to do text translation, that allows users to correct the output of the machine, so the system can learn from feedback from crowdsourcing. Document translations, you submit a Word document, it translates it for you, sends you an email notification to get it back. And chat translation. If you are chatting with somebody who speaks another language, you can use a plugin to allow you to speak multilingual chat. And you have your own user profile, so it all allows you to manage, because as I said, customization is very important. So different groups at IBM have customized the machine translation for their domain, so that they get a higher accuracy engine for their applications. So people who are servicing customers, they want higher quality on their content, so they can customize and add customized domains to be deployed in the system. And all that is managed through a system, high-performance system. We have about 15 languages, 30 language pairs. And these are some of the UIs that you can use with the system. I showed you the web browser API a moment ago. All right. So now I'm going to talk about speech-to-speech translation. So speech-to-speech translation, the person speaks in one language, speech reco, machine translation, speech out. This person hears, replies, speech reco, machine translation the other direction, and speech out. So you can have a conversation. I can speak in English, you can speak in Czech, and we can communicate. Over the last 2.5 years, the idea was to add a dialogue system in the speech-to-speech system to improve the accuracy of the communication. In other words, if the person speaks in English and the system detects there is a problem in the English, it can have a dialogue with the user to clarify what did they mean and then translate to the other side. So we're adding a dialogue system on both ends of the conversation, both on the English side and on the Arabic side, to do what's called clarification, and then you translate. And the hope here is you can achieve more effective throughput because you can solve problems at the first level instead of waiting till the end. And I don't want to get into the details of it, but this means there is a conversational interface. There is a bunch of commands that the user has to know to interact with the system, right? It's like your conversational system, okay? The most complicated command, according to our users, is this one. Replace text, this is the command, and you say the incorrect words that the recognizer recognized, and you say begin paraphrase, and you say the correct words you want instead. It seems simple to me, but it's very hard for users. It doesn't work, practically. All right, so now the block diagram is a bit more complex. Speech reco, dialogue manager, does some work, find OOV regions, error regions, and then come up with some kind of a feedback to the user, speaks to the user in English, is this an unknown word, is this a name? And I'll show you a demo of this in a moment. And after it confirms that things are good, it has a sense of what the sentence is. It can maybe replace some words with synonyms, and then send to translation, and maybe transliteration for names, and then play back into the target language, Arabic in this case. And the equivalent system on the other side. All right, so just to give you a little bit more insight into what's going on in the speech-to-speech system. So I'm going to talk about embedded grammars and OOV detection. So when the user comes to the system, he says the contractors can do. The ASR discovers the contracts need to, makes a speech record error here. The machine says, I heard the contracts need do. Say replace text or start over. So now what you want is you want the recognition to be accurate enough to detect contracts need, because that's a new phrase introduced. The user might say it. So we need this notion of an dynamically embedded grammar that constructs all possible word combinations from the speech record output that the user might pick for correction. So this is the idea of the embedded grammar. And now, if the user says replace text, contract needs, that's recognized because it's in the strong embedded grammar, and begin paraphrase, builders can. So you get the builders can do. Okay? It's a picture. I'll move on. Just give you some performance numbers. So we did 2 evaluations, or DARPA did, to be more precise. One in 2012, one in 2013, and there is one coming up in 2 months in 2014. In 2012, we used to use a Gaussian mixture model for the speech record. In 2013, we switched to a convolutional neural network. And you can see on the general sentences, as opposed to the command interaction sentences or clarification sentences, the error rate dropped dramatically to 7.5%. The majority of the benefit is due to the use of the CNN, about 30% reduction in error rate due to the CNN over Gaussians. And then the other benefits are due to better language models and other little details of that nature. We also improved a lot on spelling. Even though spelling is not used anymore in the system, we used to ask users to spell unknown words, but that's not a nice task for users. They don't like to spell, so we don't do that anymore. And the commands, the accuracy improved dramatically. And the cache, the accuracy improved to significantly also, 4% error rate. All right, so now I'm going to talk about out-of-vocabulary detection. So that's sort of one of the key functions in the new approach to doing things. So the way we do it is we build a hybrid language model. It's a language model on words, n-grams, like you know them, but we also add phonetic n-gram units. So we add bigram, trigram, 4grams of phones. This way to capture the out-of-vocabulary words by a combination of these fragments, we call them. Okay? And then we decode with the hybrid language model. So either the language model describes the region with words that are well-formed, with high probability, or fragments. Or short words. A sequence of short words also can be a good alternative for an OOV region. Okay? Then we build a confusion network. Then we add features, which are based on entropy. In this local area of the speech, what are the alternatives? What's the entropy? Just to get a sense, is this a recognized words with confidence, or is this an error, or is this an OOV? So it's a classifier based on a lot of features. And then some details about merging regions of OOV. If you find 2 OOV next to each other, you want to merge them and things of that nature. So this is an example. So if the user said, but survey it aerially. And you can see the decoded string here as a confusion network, but to survey it. And then it found Harry, Ali, silence. Or alternatively, Harry, early. Or alternatively, IX, Ili. This is the phones, the triphones, 3 phones in a row. Or early, 3 phones in a row, okay? And they each have some scores. So you can tell, based on this, the fact that the fragments showed up, this is probably an unknown region. But in reality, the unknown region is really from here to here, and the system found the region in red, from here to here. So it's not enough to find that there is likelihood of an OOV. You need to find the boundaries reasonably well. So we talk about false alarms if you find too big of an OOV region. I think the next slide defines it. Yes. So we measure performance by the detection rate of the false alarms, of the OOVs. We also penalize ourselves for false positive rate. If we say from here to here is OOV, but in reality there is a real word here that's in vocabulary, that's a false alarm or false positive rate. So that's not good, right? Because we are calling a region as OOV even though it's an in-vocabulary word. So we talk about detection rate of the OOV versus the false positive rate or false alarm rate. So this is the performance of the system. At about 5% false positive rate, we are at about 78% detection of the OOV words. And the definition of detection is 95% overlap. In other words, we found an interval that overlaps at least 95% with the OOV region, the correct OOV region. So we really found the word, essentially. Oops, sorry. So this is the results from phase 1. Then we did some improvement by using a set of Gaussian mixture models, CNNs, and more advanced features to get these kinds of curve. So this is the original curve with the Gaussian mixture model, the red curve. Switching to CNN improves things, and switching to richer features in terms of the decision making improves things a little further. So we are at about 80% at the 5% false alarm rate, 80% detection of OVs. And this is our operating point typically. We try to operate around this point because we don't want to produce too many false alarms. This was on English. The same results hold for Arabic, except that the performance is a little worse. At 5%, we are more like 60, 65% instead of 80%. It's a little harder. Also, we haven't worked on it as much, right? It's always you need to work on the problem to get all the tuning correctly. Okay. I wanted to show you an example of this. So this is an actual conversation during the evaluation in phase 2. So the user is an English speaker in this case, said,
"Good morning. My name is Sergeant Truman. I'm looking for information on a patient named Ashkar."
So you can see the fragments. Ask, cow, silence, silence. That's typically a good indication that there is an unknown word here. So that last word was an unknown word to the system. Now the system detected this and said this to the user.
"I am not sure about
Ashkar.
if it is a name, say it's a name. Otherwise, say begin paraphrase or start over."
In this case, it's a name, so the user said,
"It's a name."
Because it's a name. But if it was not a name, he would have said a synonym, travel, some word. And so on. If you want, let me play this. This is in Arabic so that you can see what happens. It's going to speak a lot of Arabic, and then it's going to play the Ashkar in English.
Ashkar.
Okay? All right. We can go. There is lots of nuggets in this stuff, Interaction is very rich very quickly. But I'm not going to spend more time on it today. I'm going to skip that. All right. In the remaining 20, I guess I have 10 minutes because you want to stop at 50. I'll do the post-editing. This is actually quite a good success story in terms of the value of current machine translation for business processes, but fundamentally the localization marketplace, where people are spending, there are huge numbers, I don't know which one to believe, but more than $15 billion a year on human translation. So any improvement in the productivity is a significant business venture. So IBM has its own budget and work and organization to manage human translation for IBM. They do about 3 billion words total. About 400 million words of them are new every year. 60 language pairs. And they have 24 centers to manage the translation processes, and they work with 115 companies that do localization. And these companies hire the translators, right? So it's a huge operation. It's a lot of people, thousands of people who are working in a production mode. So we injected, and IBM has been very focused on using technology to improve that process, in terms of managing the file systems, the tools. All the IBM translators use an IBM tool to do the translation in the tool, as opposed to their own. So it's all managed quite heavily. Fundamentally, to have the curve on the left, where they don't like to release the numbers, but their cost per word are decreasing on a yearly basis. So they're trying to improve automation tools to reduce the cost on a per word basis. And but because they translate, and over time you have more things translated, something comes new, if it's translated before, you can reuse. It's called translation memory. That also is increasing over the years. All right, so they were willing to explore the use of machine translation. They had done it in the early 2000s, and it was not successful. It was not successful, just leave it at that. And they were very worried when we said, let's try it again, because they don't want to, screw up the business, so to speak. So we said, let's try it as a pilot. And we did a pilot with them using the IBM tool called Translation Manager. It's a tool that all translators use. And it has the notion of an exact match. You get a sentence to translate, but you already have translated the same sentence before, maybe in different contexts. So there may be multiple target translations for the exact match, because it depends if it's product 1 versus product 2. There are lots of outside the sentence context that can change the translation. Then the next category is fuzzy match. You have a sentence that's very close to it, not exactly the same, but maybe 90% overlap. So it's probably good for you to edit that fuzzy match instead of doing it from scratch. You can end up being faster. That's the benefit of the translation memory. And the third case is no proposal. Nothing is close enough. Everything is very far from the previous translation, so we call this no proposal. And the new thing that we added is we added machine translation proposals with the letter M for these proposals. I already described the fuzzy match. So you want to translate Hillary in Mexico, and you have a sentence, Hillary Clinton in Francia. All you have to do is pick the fuzzy match of 75%, and then change France to Mexico, and you're done. So this is the process. So you have a fuzzy match, you pick it, and then you change a word, and you have post-edited it, and you have now a translation that's fast and doing it from scratch. Or you can use machine translation if it's perfectly close or closer than the fuzzy match. I'm going to skip this. This is just a more complicated sentence of the same concept, that sentences can be similar. They have extra content in the green, or they're missing content in the pink, and you have, as a human, to pick it and fix it. So that's the post-editing of the fuzzy match. So it's actually quite these people are really highly qualified and specialized. They can see these things much faster than we can see them, because they're used to this stuff. They're very, time is critical for them. They don't want to be bothered with extra stuff, because they're very focused on trying to get it done quickly, because they get paid by the word, right? So the faster they can do it, the better for them. Okay, this is the screenshot of the tool. I'm going to skip. So what we did is we built document-specific machine translation system. So we took the concept of customization to the extreme. If we want to translate this document to translate, we will build a specific machine translation system for this document. So we get the document, we find from all our parallel corpus the closest subsample of sentences that match it, build a system, translate the system, and this is the new machine translation output that's customized to this document that we send to the humans along the fuzzy match proposals. And we did this for a period of 10 months in 2010, and we did over 4.5 million words, which took about 1,700 person-hours of human labor across 16 translators. And we measured everything they did. We know every character they picked, how many milliseconds it took, so we knew exactly what was going on with these data. So this is some statistics on this. Let me just skip that for the sake of time. I just want to focus on 2 slides here. So as I mentioned, some sentences are fuzzy matched and some are no proposal. This is the actual use. When it is fuzzy match and they pick the fuzzy match proposal, we count it here. When it is fuzzy match, but they do it from scratch anyway, because they feel it's faster for them to do it from scratch, it's in this bucket. And when there is no proposal, they have to do it from scratch, it's 183,000. So you can see 47% of the time, they did not use the MT proposal. When it is fuzzy match and there was an MT proposal and they picked it, we count it here. And when there was no proposal and they picked the MT to start with instead of doing from scratch, we count it here. And you can see they use 53% of the time the machine translation output. This was very encouraging for us, because the users are voting with their fingers. They're picking the MT proposal to do the work. Whether they are faster or slower, they do not know. They think they are faster. It's another important thing. But we were very excited at the time, because we did not believe it would be that good, actually, because I remember the history. IBM was a little bit worried about this. So let me skip this slide. Let me get to the speed number. We also, since I said we keep track, so when we give them a folder, a project to translate, we on purpose remove for 10 to 20% of the sentences the MT proposals. This way we have a placebo. We can control without MT, with MT being present, to see what the statistics are, because the speed depends on the content, right? Easy content is faster than faster content. So this is the way to control so that we have accurate measurements in terms of speed. So if we define that when they do it from scratch to be 1 word per unit time, okay? If they have a fuzzy match proposal, they tend to be 30% faster, 1.3 words per unit time. But when MT is present, this is doing it without any MT. This is the placebo case, right? We don't show them any MT. When we give them MT, and they pick when they use MT. Not every time they use MT. I showed you the percentages before. But you can see on the no-proposal sentences, they're 41% faster. And the fuzzy match sentences, they're 31% faster. So even in the fuzzy match case, the MT does help because things are even better with MT. Okay, so this was quite a success. And since then, they have 5 languages in production: Spanish, Italian, simplified Chinese, Portuguese, and French. And we started 2 years ago. I think it is 2 years ago, a year and a half ago. 3 languages in pilot: traditional Chinese, Japanese, and Arabic. So I focus on the lower curve. This is again showing you the percentage MT, NP, and this is for the non-proposal case. How much MT was used, how much from scratch was used. And yellow is these are sentences we don't analyze. Because when you take a coffee break, it takes 10 minutes to do a word, right? So we filter out all the events that are much longer or much shorter than the expected value. And you can see on Italian, they have 40% usage of MT. On traditional Chinese, they have 80% use of MT. And on Japanese, we were very surprised and very happy, actually, at the time, that they are 30% using MT. We said, wow, we know English-Japanese MT doesn't really work. So what's going on here? It turns out they are slower. Even if they are using the MT, they are slower, right? So if you remove the MT, that would be faster. So the Italian and traditional Chinese worked very well. Japanese did not show any improvement. So we said, what are we going to do? You know, we still wanted to see if we can do something about it. So the basic idea is, why don't we not show the MT all the time, but show it with a confidence metric, so that the system tells the user when it's worth looking at the MT. Because the problem is they were spending a lot of time looking at the MT to decide whether to use it or not, even though they found good uses of it, but they wasted so much time on the other segments where things were not even close, that the net benefit is negative. So by adding a confidence metric, and I'll explain in a little bit more detail what that means, and this is different from quality estimation, because in confidence, we can look at the internal scores of the machine translation engine. We don't only look at the source and the output, we also look at the details inside how we translated it to decide if we are confident in the translation. So there is a lot of research on quality estimation. This is a little different. This is confidence estimation. They're related, but not the same. So I'm in negative time now. To go quickly, there is a bunch of features, internal decoding features, 17 and 9 external features, and they help performance a little bit to predict quality. Or to be more precise, predicting if a sentence is more than 10% H-tur. So given the output of the machine is predicting this sentence has more than 10% edits needed to make it correct. And the way we use it with the users is we show the MT all the time, except now we say high confidence, medium confidence, low confidence, and we instruct them only use the A confidence, the high confidence ones, for post-editing. Don't spend your time on the others. But we have found it to be useful to show them the others because sometimes they extract fragments from them for phrases. You know? So it's good to show it, but now they know where to spend their time. Because the machine is telling them focus on the high confidence and so on. I have the statistics actually on what they do. But the point is that now they can decide when to spend their time and where. And this leads to a good result. I'm going to skip this. I'm going to simply summarize this by saying that confidence estimation has to also be document-specific. It doesn't work if it's document general. You really have to retrain your confidence estimator on the specific document you are translating. And it's in the papers, you know, we can look at the details. But this shows that the correlation within document, our adaptive confidence estimation is about 0.53, whereas cross-document is 0.1. So you really have to do document-specific confidence estimation. So not only is the system document-specific, but the confidence estimation is also document-specific. That's what made it work for us. And here, I showed the results on Japanese now. It used to be, the red curve used to be high, and now it's about 9% faster. And that's really, we're very excited about this result, because Japanese is really a very difficult, English-Japanese direction is a very difficult language pair. These are more details. I'm going to skip that. Basically, this shows that the speed is improved on easy sentences, on medium sentences, and on hard sentences, actually. You get a win, but the win is bigger on the easier sentences. And text leveling for MT is the final topic, which essentially, in the context of language learning, if you want to learn a new language, the system with self-service, the system has to find text that's appropriate to your level of knowing the language. So you need to level the text to the difficulty level for the learner. So we have methods for automatically detecting the level of difficulty of a piece of text. And our contribution was to, people used to do it by building a big supervised set for each language and building a system. We basically said, let's build an English system and use MT, translate everything into English. And you can see that our accuracy with the English, with the machine translation is 57%, whereas the baseline accuracy is 65%. So you don't lose a lot by using machine translation for text leveling. And this is a lot cheaper. And I think that's it.
Thank you very much, Salim, for this very interesting talk. We have time for questions.
None of the languages you showed us were from the Slavic group. Are there any data of the performance from English to a Slavic group because of the rich inflectional morphology that makes usually a problem for the translation?
Right. So we have English to Russian. We have not used English to Russian in post-editing because that's not a significant IBM target language from a human translation point of view. The quality of machine translation on English to Russian is probably, so I categorize languages into A, B, and C. So it's in the B- category compared to, I would say, all the Romance languages and Arabic are in the A category now. Arabic used to be in the B, but now it has become so good that it's in the A category. Even though Arabic has also rich morphology, but not as rich as the Slavic languages. But it is a challenge. I would say this is still a work in progress, the rich morphology. We've tried many ideas in terms of taking the words, finding the lemmas, predicting the lemmas, predicting the morphology, the ending and all this stuff. Still a work in progress.
I have a sort of similar question. You didn't mention, probably on purpose, Google Translator. And also we have
Did
this...
you notice I had something called online aid?
But we have the same experience, say, with Google Translator when translating from English to Czech.
Mm-hmm.
Problems.
Okay, now, in fairness, I would say you're probably going to have problems with all machine translation systems from English to Slavic languages. Fundamentally, anytime you go from a poor morphology language to a rich morphology language, you have a lot more hidden information that you have to reconstruct. And that's why Chinese to English is difficult, actually. Chinese has a lot of hidden information that you have to produce English, So that's always going to be a challenge. So I would say across all the machine translation systems, you will discover it's harder. And so it's going to be, again, it's a curve, right? There has to be investment to work on it. There's no magic.
On that. Are they in the direction of a pure statistical machine translation, or
Okay.
Incorporating?
This is the old debate. So everything is a statistical system, but we use all the linguistic resources you want. But the key is that the whole thing is embedded into a data, learning from data. Okay. So you are welcome to bring in all the linguistic features you can think of, but you really need to train on data to prove which ones are really worth keeping versus not. So I sort of hinted at this with the rich feature, the big maximum entropy model. We throw at it all kinds of features. We even use, in the Chinese system, which I did not talk about today, what we call parse forests, right? So because the parsers in Chinese are not very good. So to hedge our bet, we want to have multiple parsers. So we go to the extreme of parse forests, and we basically translate chunks of the parse and use that to help us locally do something. So I would say, throw at it anything you want, but everything is a statistical system, including the old rule-based systems, I think that this dichotomy is a fallacious, for me, this dichotomy is a fallacious dichotomy. Because, I think it is clear you want to use data to learn the parameters. Even in so-called pure rule-based systems, they took weights, So it's like a poor man's statistics, Okay? You got me on record now.
Because my question would have been, are you sure you're doing statistical machine translation? So this question is now answered. So basically it's a data-driven system.
Right. But don't say the word data-driven in a negative way, right? It's a probabilistic model at the end of the day, right? So be careful. Yes, of course. No. No. No, it's not true. This is all machine tuned. This is all data driven. Nothing is, nothing is a strong statement. But this is all tuned by optimizing on the data, TER minus blue today. In the old days, we used to do blue. So we basically, whatever parameters are in the system, they are trained either by maximum likelihood for some components, and then when we combine the multiple components, we do discriminative training by optimizing TER minus blue on a tuning set. Okay, so it's all data-driven. Very important. You cannot do it by hand. I'll give you an example. When I build a system for every document, who's going to spend the time to tune what the weight is? Nobody can do that. We build a system we build many systems every day.
Yeah, sure, but for example, what you've shown on the web page when translating the Arabic.
Yes.
And you said there are problems with, like, you get this one, it got right on him or something, and you might have get it. So, for example, if you tune that, so someone has to look at it.
Oh, of course. Of course. That's the linguistic knowledge, right?
Yes.
So we do error analysis to identify phenomena that we need to add to our statistical model so that to capture the phenomenon we want to capture. So, of course, there's no magic that way. That's why we put in parse trees. That's why we understood that we want to do functional tags so that we can find the subject as opposed to the noun phrase, right? So, that's right. And then we define the feature. So in that sense, yes, of course. That's the way the linguistics comes in. Sometimes people refer to it feature engineering. It's better than that, hopefully.
Thanks for the interesting presentation. I have a very general question regarding speech-to-speech translation. And it's my question all the time. When there is a speech, do we have to pass it through ASR and have text and translate? Is there any way of just working on sound level?
Yeah. I have to be careful what I say. Let me make the following comment. There are people who have tried to do from non-word models to the translation. I'm a big skeptic on these things. We just, in the previous question, we were saying we want to introduce linguistic structure. So I would say use the morphs of the language as at least, okay? So I'm a skeptic on other approaches for now. Remember, the way statistical models work, they get a huge win when your feature representations is close to the data that you're going to approximate. Because at the end of the day, it's an approximation problem. So it's to your advantage to be clever in picking a good approximation framework so that the parameters can sharpen up very quickly with training data. So that's the way I look at these problems.
Other questions? Okay, so I think we can thanks again.
Thank you.